It's my distinct honor to introduce Dragos, who I'm sure many of you have already met, for his presentation, and then we'll get into some more ChemAxon science.
Thank you. Well, glad to be here once more. Bad news for those of you who didn't attend the previous meetings. I will have no time to give all the details about our website saga. I'll just intend today to present the latest developments and the latest studies we have made. Okay, so just a quick wrap-up for the chemoinformatician, nothing new. It's a site for similarity-based virtual screening. We all know what it means. We'll have a query, capital M, a bunch of candidates, and the query is active, and we hope that the similarity principle will fish out actives as well. Therefore, we need to define similarity. So there's a similarity score. We used to call it sigma, so don't be scared of sigma. Obviously, molecules are placed as points in a descriptor space, and sigma is the metric or the score of this descriptor space. So far, so good. Where things get more complicated is the similarity radius or cutoff, because we need to know at what point we stop considering those neighbors as close enough, okay? And so what we want to get are virtual hits. That means the candidates within that sphere, and these will contain true and unfortunately also false positives. Okay, now for the server calibration we went to Campbell, and we got by Jürgen Bajorat, who did the cleaning. Thanks, Jürgen, he's not here. 165 sets with at least 50 molecules of measured pKa for each target. So we're discussing thermodynamic affinity. These are very high quality data. And out of each set, we considered queries, that is the top of the list, the topmost actives, but also a series of average queries somewhere in the middle of this list in order not to bias the results by considering only the top nanomolars. And then we use decoys, something randomly picked out of zinc. And as far as the web server goes, today it exploits 1.5 million of commercial compounds of various sources, but also includes the Campbell subsets as a pool of reference molecules for annotation. You're always happy when you start with a NK1 inhibitor and then manage to fish out other known NK1s, because it gives you confidence that the others might be actives as well. Okay, so this is the web interface. You see you have the first topic to decide on what compounds you want to use. So you can address the combination of subsets you want to check. That's pretty straightforward. And as far as the descriptor spaces go, so here is the main contribution of ChemAxon lays behind the descriptors. There's a help button on the site. The descriptors have been published. They're typically substructure counts of various types, including fuzzy pharmacophore triplets, but also sequences and branch fragments that can be or not colored by pharmacophore, which again calls the pKa plugin in order to set the pharmacophore flags properly and all that. But as far as of today, you only need to know that these are feature counts, so they're integer descriptors. And to exemplify, I will simply refer to the number of phenyls in the molecule, although we never count the phenyl rings. It's a bit more subtle than that, but so far so good. Okay, so the similarity scoring means we want to compare the descriptors, and people are mostly used to deal with binary fingerprints, so there's a little dictionary to translate binary language into integer vector language. This is the number of bits populated in the descriptor, so the number of present features, and it's correlated to the norm of the vector in integer speak. The number of common elements, which amounts to this, the number of elements exclusively populated by capital M and absent in small m, and so on and so forth. You know Euclidean distance. It has a problem. It is heavily size dependent. If you take two small molecules, there's no phenyl rings in the water molecule and neither in methanol. So if you don't have features, you can't get this score to increase. Small molecules will also always be artificially similar according to Euclid. That's why, well, let's try to scale down by size. And we also consider these two. This is actually the RMSD of the two vectors. This is the same but in block distance, in Hamming distance. And then we had another issue. If you think about it, a molecule without phenyl rings and a molecule with one phenyl ring, that's a huge jump. It's a real culture shock. But the difference here would be 1. Whereas a molecule with 4 phenyls with respect to one with 5, that might be a detail, but the difference is still 1. So there's something special about the first occurrence of a fragment, and we could take care of this by including these exclusivity weights here in the score. So we got the weighted corresponding scores. And then, of course, you have the one and only Tanimoto everybody knows about, and our favorite Tversky metric. So Tversky is not really a metric because it's not symmetrical. If you look at this alpha here, you can see that Tversky helps you to distinguish between the two situations. I mean, if your active molecule contains a phenyl ring, then somehow that phenyl ring is special because it appears in an active, and you know that at least it's not incompatible with activity. Maybe it's very important for activity. You cannot know it at this point, but at least you know it doesn't do any harm. So if you delete that phenyl ring, you are at risk of losing some activity. On the other hand, if you don't have the phenyl in your query, but it appears in the candidate, well, introducing a phenyl ring could cause different kind of effects. Of course, it could bang against the site and make you lose activity, but it could also harmlessly dangle out of the site in the solvent and produce no effect at all. You see, the two situations are different, and by playing around with alpha, you can highlight one or the other. Now, you don't want to fine-tune alpha. We just considered, instead of fine-tuning alpha, we considered 3 different Tversky metrics where we just set alpha, 0.9, 0.7, 0.3. 0.9, 0.7 are query-oriented metrics, so which penalize if you lose a feature from the query. 0.3 does the other way around. It will penalize if you try to introduce novel features. And, well, in the paper, which will hopefully appear soon in GCIM, one of the referees had a remark with practically Tversky looks intellectually appealing, but nobody uses it. I did a literature search and found virtually no hits, and the hits that were there were technical papers about Tversky. And the referee said, hey, wait a minute, you can't say that because all the software suites include Tversky, so somebody must be using it. So there's something to this argument. So if you do use Tversky but never dare to make your coming out, let's meet in the damp basement room, sit around the table and stand up and say, hi, my name is John. I was using Tversky for 3 years now. Okay. So now comes the tough part. So what do we do about the similarity cutoff? It's, for Tanimoto, everything settled, 0.15 or 0.85 in similarity. And it was it in Bournemouth in the EuroQSAR? And I heard you giving a lecture about take care, it's not as simple as that. And I said to myself, hey, why should anyone believe that this is true to start with? But actually, managers need to believe in this kind of myths like Tanimoto or Lipinski in order to keep up the illusion of believing that they know where they're going. So, but okay, believe it or not for Tanimoto, but fortunately there's no other rules for the other metrics. So you have to do something about it. Let's try to infer some similarity, some reasonable choice for this similarity radii. And how do we do it? Well, you have to go into neighborhood behavior. Let's see how the similarity-based screening works. So if you have here pairs of molecules and you rank them on the x-axis by their experimental property dissimilarity. So here the lambda was again defined according to common sense. If the candidate molecule has a pKa within a half a log or better than the query, we're happy. Of course, you will not see a medicinal chemist that shouts at the chemoinformatician like, what, I gave you a micromolar lead and you come with a picomolar hit? You call that an application of similarity? They have 6 logs of difference, you're fired. I don't think so. I think the chemist will be quite happy. So this score is again asymmetrical. And well, on Y we just rank the pairs by calculated dissimilarity. And we'll have a cutoff. I'll distinguish the true positives and the false positives we want to avoid. But we also have these potentially false negatives. Why potentially? Well, because structural similarity is by no means a condition for activity similarity. You can have the same pKi and be wildly different. There's a lot of confusion about this, but remember that although all the Al-Qaeda members are Muslim, not all the Muslims are Al-Qaeda members. So similarity principle is a one-way inference, not an equivalence, okay? And let's set this score. We count the false positives and we count these potentially false negatives. And because the false positives are more of a trouble, we'll scale them up, let's say by 5. And we report this to the expectation numbers that would have been obtained at a similar selection size by completely random selection. And what happens? Well, if our cutoff is very low, we select 0 molecules, and then whether you select 0 molecules randomly or rationally, it basically comes up to the same thing. Everybody here will be false negatives, and omega is 1. As you continue, and if your metric makes chemical sense, you would like to encompass this forbidden zone here, where you have a deficit of false negatives because the similarity principle operated, and omega will decrease. And if you continue, then obviously you'll select everybody and you come back to 1 again. So this is a reasonable choice for this similarity radius. Now we did statistical tricks because if you have this kind of shape with real relevant metrics, and if you inject random numbers instead of similarity metrics, you get this kind of noise. So you would like to correct for the standard deviation here, and we inverted the curve as well to have a maximum and define this ascertained similarity optimality criterion, which maximizes at the optimal dissimilarity cutoff. So far, so good. So what did we do? For each target, we set the database to the set of known actives plus decoys. We took each query, each descriptor space, each similarity score. We calculated the similarity scores. We did this scan over the cutoff range and found S optimum. And then, according to the ascertained optimality criterion, we decided whether this virtual screening was a failure, unacceptable, or a great success. Well, we just binned it by several values. And we made some analysis. So how does it look? So for example, if you look at the percentage of Tanimoto-based queries that reached good optimality levels, so these are only successes, with respect to the optimal cutoff required. You'll see that this optimal cutoff varies a lot from query to query. And not only that, the distribution of the values varies a lot between two descriptor spaces. So in this three fragment count, you could get away with Tanimoto 0.15 because you would have selected all these. That's a reasonable amount. But in fuzzy fingerprint space, the typical cutoff should be much, much larger than 0.15. And we use these kind of distributions in order to teach the web server how to rank the hits by quality. Because when you come with an unknown query, well, okay, so how far should I look in the list? You could say, well, if you use the green descriptor space, then everything up to 0.12 should be top hits. The others will be good. So just bin this histogram by percentiles and define hit categories. So after a certain point, you're sure that you can ignore the molecules. And with the other descriptor space, these ranges will be different. So we'll have, for each descriptor space and for each metric, we'll have a tuned dictionary on how similar is similar. And then, if you look at it, how do the metrics compare? Well, astonishing enough, the alpha past 0.5 Tversky do an excellent job. They actually outperform Tanimoto, which is in trouble. It cannot really defend its world champion title in this benchmarking study. And well, Euclidean and Assimilated do a less good job. But well, Euclid was a Greek, so you see how much of an economic impact the choice of the wrong metric can have. Stuff sinks. If you want to go chemical and see what does Tversky mean for me, well, see, this is an NK1 active. Tanimoto will retrieve typically this kind of compounds which are obviously related, even though there is some scaffold hopping in there. But you see, it's the same size, it's the same complexity. This is about as far as Tanimoto's originality could go. So it allows for a little bit of growth here, but you still have the positive charge conserved. This larger ligand with two positive charges would only be retrieved by Tversky, which is more permissive with respect to allowing new features to come in. So you can see that there's a certain dependence on the target class. So if you look at various classes of GPCRs and kinases and all that, you'll have certain fluctuations, but there's no time to go into those kind of details here. It also depends on the query complexity, which we measured simply by the number of pharmacophore triplets that are populated in each query. And you can see that complex queries are, in general, less dependent on the metric you choose. Simpler queries have more sensitivity to the choice of the right similarity score. And conclusions to jump in. So you do have a very nice behavior of Tversky, and we can use it. It's not a matter of, I guess people were just scared by that alpha. You don't need this more or less intelligently guessed value of alpha will do, such as 0.9 or 0.7. Just put it in there and try it out. It's quite robust. And there's a lot of analysis in the paper I just referred to. It should be accepted soon, I hope. And nevertheless, even with Campbell or not Campbell, there's still a lot of bias in our study, and we pointed it out in the article. There's no chemoinformatics without bias. For example, there's a target with excellent optimality criteria, but when we looked at the structures, we could find the linear regression between the pKi and the length of the SMILE string. So you just have to search, and you will find this kind of tricks. So the main message here is not necessarily the this fine analysis, but the protocol. So this is, in our opinion, a way in which you can calibrate a similarity server, and you could try it out. Well, not all of you at the same time, please, because it's a poor little machine which harbors this server, but go on and play around with it, because I think there's no other publicly available machinery supporting Tversky these days, and we also have the cool descriptors which are due to the ChemAxon developers toolkit. And I guess I'm done by now. So, thank you.